AI has solved many of our simplest games. In chess and Go and Atari Breakout, humans have already become second to the superiority of artificial intelligence. Yet, the best attempts at AI development to solve roguelikes remain orders of magnitude worse than the performance of human players. Roguelike is a subgenre of role-playing video games characterized by a dungeon crawl through procedurally generated levels, turn-based gameplay, grid-based movement, and permanent death of the player character. Most roguelikes are built on a sort of fantasy narrative, which has far-reaching effects on gameplay. Spells, weapons, traps, and anything you could possibly think of probably already have some sort of implementation in a roguelike game somewhere. These very human narrative twists on roguelike games present a uniquely difficult challenge for AI developers to tackle. Our project can be split into two halves. In the first half, we create a simplified roguelike game, and in the second, we train the AI to play it. Welcome to our presentation, and we hope you enjoy. Bail was developed with the key functionality of being easy to pass into the AI engine in mind. Original versions of the game used rather simple native lists to store the board state, but as we expanded the functionality to encompass many different entities, tiles, interactions, and logic, we quickly came to realize that functional programming was insufficient to organize everything intuitively. This is an overview of the classes involved in the game. The key component of the game engine is the game class, which manages the game state, logic, and interactions between entities. Every turn, it checks for tile callbacks and cycles through each of the entities, which make their individual moves accordingly. Games must be initialized with a board class, which then, based on generation type, will call the correct board gen class and create the tile instances. Board manages the state of the tiles and has a number of helper functions implemented which are used in other classes. Tiles hold information for display in the GUI and have callbacks to interact with the game. The entities package is a fairly large package which holds every possible entity in the game. This is grouped into players, enemies, and neutral entities. Finally, controllers manage the players and run them through games in order to determine their effectiveness and improve them. With the main structure out of the way, we can run through some of the interesting aspects of the game. The board generation has two steps. The first defines the structure of the level, and the second configures it into a playable level. The board generation algorithms only differ in the first step. The first board type is caves, which uses cellular automata to generate a huge cave level. It first fills up the map randomly with walls and empty spaces. Then it goes through each tile and checks. If the 3x3 region around each tile contains 5 or more walls, or the 5x5 region contains 2 or less walls, become a wall, else become empty. Repeating this 4 times creates a turbulent map, as islands spawn where there are larger empty areas. We can then run the same rule without the island creating section in order to smooth out the caves. For aesthetic purposes, we then use the same algorithm to create water shapes. The second board type is rooms. In this algorithm, rooms are placed randomly in a map with randomized width, height, and position. If a room overlaps with another room, it is just deleted. Rooms are then connected using strictly straight passages, using an algorithm to keep track of which rooms have been connected. After all the rooms have been made, the inner walls of the map are lined with metal. The last board type is custom, which is loaded from a map file. We use this to create debugging maps and other different game modes. After the board is generated, the map is flood-filled and any empty tiles that are disconnected from the largest chamber of the level are filled with granite. The start and end points, if not placed by the board generation algorithm, are placed randomly at least 100 tiles apart. There are 6 non-player entities implemented in the game, 2 enemies and 4 neutral. Firstly, enemies largely act in the same way. If they can see a player, they will target it and try and kill it. If they don't, they will target random squares on the board and move to them. If an enemy loses track of the player, it will move to the last place seen. The 2 enemies, James and Rubber Duck, are only different in speed. James can move twice in one turn, whereas Rubberduck can only move once. Next, the neutral entities. The most important neutral entity is Fredwood the dog. Fredwood behaves much like an enemy as it wanders the level and tries to find the player. It will then move much like an enemy towards the player, but when it is within a certain range, it pathfinds towards the exit, guiding the player along. The next three neutral entities, Cactus, Ball, and Box, are all blockages which can be used to divert enemies. Cacti are destructible and disappear when you attack them. Boxes are non-destructible that can be pushed. And finally, balls can be pushed and continuously roll in the direction they were last pushed. Balls can be taken advantage of to boost speed, while boxes can be used to block passages. However, balls and boxes were not used in the AI training because their utility is less straightforward. We made 3 main attempts at creating an AI to solve the game. In the first attempt, we copied an online tutorial for a snake genetic algorithm and created one where each chromosome defined a multi-layer perceptron. At the input were 9 integers representing the tiles that surrounded the player, followed by one hidden layer of 5 neurons and one output layer of 9 floats. Crossover was just hacking the different layers together randomly, and mutation was random replacement of weights. At the point of creation, the algorithm was only meant to do some sort of pathfinding. The fitness function was how close it got to the exit, and as you can imagine, it did very poorly, essentially learning how to walk in one direction towards the exit. The next algorithm was created after we realized a few things about our game model. Firstly, storing responses to each game state as used in other simulations such as Eater's World was infeasible, as there were 28 to the power of 25 different possible states if we wanted the player to interact with objects 2 spaces away. Secondly, since we allow for diagonal movement, the space around the player is geometrically equivalent to a circle. Lastly, enemy responses are not really dependent at the angle at which they occur, only the distance. With this in mind, we had an idea to flatten each individual interaction into one dimension, which would bring our accounted for cases into a reasonable size, and then expand out the interactions again in order to have them interact in some way. Each entity at each distance would have a vector which would be equivalent of an instruction to the player. For example, a vector with a large magnitude pointing away from an entity would be an instruction to move away from the entity. These vectors, stored in polar format for easy rotation, would then be translated into Cartesian coordinates and summed. In retrospect, taking the sum of these interactions was probably not the best idea because it meant that they could destructively interfere, but the idea was that the AI would somehow learn to use these interactions to its benefit. After a few hours of training, it was evident that this would not be the case. The fitness of the player was improving, but not at a rate fast enough. What you see here are visualizations of the vector brains which our training produced. The first brain was able to reach 1000 fitness because of its large James vector at distance 1, which allowed it to prioritize killing the highest scoring enemy, hence racking up large scores. It also had a James 2 vector, which allowed it to kill rubber ducks. Meanwhile, the second brain reached about 500 fitness by killing rubber ducks and spreading the other vectors out widely in order to maximize score from visiting new tiles. In the end, the best models we could make using this method were able to kill enemies, but were inconsistent. With some improvement of the mutation functions and more computational resources, it may have been possible to make this model work, but we moved on. The last attempt we made was meant to tackle the overwhelming search space and interference between vectors inherent in the vector player. The vector interactions of the player are replaced with potential moves and a priority value. A random move with the highest priority value is chosen and executed by the player each turn. Despite, or because of the simplicity of this model, the priority player achieved much better results than the vector player in a much shorter time. After only 10 generations of training, the player learned to kill all the enemies and reach the exit. However, the best brain of Generation 20, as shown here, still has some very strange results, such as a tendency to sit still when adjacent to the exit, or a very high priority move sideways when next to a wall. Although it is possible to think of plausible explanations, these are likely caused by insufficient training generations. This concludes our presentation. Although there was much more we could have covered, my wrists are cramping from typing the script. We have a long list of improvements for future work and might continue this project beyond the deadline to get a more in-depth understanding of the capabilities of our models, as well as the effect of different room generations or parameters.